Welcome to another edition of the MVC screencast. I guess we'll call this one 0.2. I just want to do a quick example from optimization, in particular the unconstrained variety. Let's look at this example problem. Find the minimum volume that can be cut off in the first octant by a plane through the point 1, 2, 3. I like problems like this. The question's pretty succinct, yet it belies a good amount of complexity. First off, the reason you know it's an optimization problem is right here. The word minimum gives it away, and the fact that they ask for a minimum volume, already we're there. We know which quantity it is we're going to want to optimize, right? And that's volume. The rest sets up the geometry of the problem, right? It's cut off in the first octant, okay? So we're in three-dimensional space here. We're dealing only with x, y, and z positive. That's what the first octant means. And we want a plane through the point 1, 2, 3. So, of course, it helps to draw this. I have this little model mocked up already, but you can do this in your mind or a couple of sketches just to even realize that this is a problem to be optimized. We want the minimum volume, so we want to cut off as little volume as possible. But we have some control. We have this plane. It has to go through the point 1, 2, 3, but it can move around a bit, and there are clearly different answers. Our configurations are possible as we move the plane, keeping it through that one point. Let's look at it from another angle here. We see there are different possibilities for volumes, and you get some intuition that there's probably a smallest somewhere here. The first step, as in all optimization problems, is to identify the objective, that is, the quantity to be optimized. We've already stated this is volume, so we want to give it a name, B. Makes sense. Now, for the object in question, it's actually a tetrahedron, right? We've cut off the first octant along the three axes. So the volume of a tetrahedron, if you've forgotten, is actually somewhat easy to compute. First, we'll label the three sides, length, width, and height. And we'll start off by saying that the volume, we get the area of the base, which of course is just a triangle. That's where this 1/2 length times the width comes from. That's not the end of the expression, though. That's just the area of the base. And so the volume of a cone-shaped is the area of the base times the height over 3. As you may recall, we can neaten that up, of course, into 1/6 length times width times height. So now we have our quantity to be maximized as volume here, and we have some choices to make. One option would be to realize we need our plane to go through the point 1, 2, 3. So we could try to take the Lagrange multipliers approach and set up a level surface, a function g, that will determine that the plane through our intercepts L, W, and H will contain the special point 1, 2, 3. But if we think about it, that sounds like a pain, right? We have to set up a bunch of equations to make sure it goes through that point. So we're going to take a different approach here. We're going to start by saying, wait, I know what a plane through the point 1, 2, 3 looks like. It has this form: a times x minus 1 plus b times y minus 2 plus c times z minus 3 equals 0. Every plane through that point has that form. So we can pick the coefficients a, b, and c. But we can do even better when we realize that that normal vector, a, b, c, can be chosen to be any length at all. So I can actually just say, well, let's just take that first coefficient, a, and ensure that that thing is 1. And what we're left with is two control variables, b and c. We can choose those arbitrarily to be any number. Turns out they have to be positive. But they can be any numbers, and we'll always get a plane through the point 1, 2, 3. So we control the variables b and c. We just need to figure out what this volume is in terms of b and c. For that, it's a simple exercise in algebra. First, we'll figure out what the x-intercept is, right? That's L. So we'll set x equal to L and y and z equal to 0 in this plane equation, and we'll simply solve for L. 1 plus 2b plus 3c. We proceed for the other intercepts, right, w and h, respectively, in the same way. We'll set y to w, the others to 0, and solve. We just get that b denominator. And similarly for z. Once we have this, there are L, W, and H. We can plug them back in to our volume form up there, and we see that we get this nice form V in terms of our two control variables, B and C. Let's go back to the picture. So we've got our function of two variables written out here, and now this is a regular old unconstrained optimization problem. We can choose B and C really to be any real numbers, although if we think about it, we'll only want positive answers, as they're the only ones that will give us positive intercepts. But we're just going to look for critical points at this point where the gradient of V equals 0, and it's a good exercise to do this by hand. You should be able to do it and solve the necessary algebra. But in this screencast, what I'm going to do is show you how Mathematica can save us some time by automating these things, and it's good for checking your work and for doing a bunch of other examples to make sure you've got the setups right without getting bogged down in a whole bunch of algebra and making mistakes, and so on. So the first thing we need to do is simply define our function v. Mathematica has a lot of ways of defining functions, but I think the most straightforward is to use the function, which takes two arguments. You got a list of the inputs, we'll do B and C here, and then just what the output is. So we'll just enter that expression. I'll use a couple shortcuts, but you can do it in the usual way. 1 plus 2b plus 3c, all cubed, over BC. Now be careful to put a space between B and C if you want to multiply them and not just refer to a variable called BC. Put a semicolon at the end. I don't want it to print any output. There. Now V is well defined. We can test out some values by simply sticking in values for B and C using the square brackets. Shift enter to evaluate. All right, there's our volume for values of 2 and 3. To find the gradient of V, of course, we need to take partial derivatives, and there's a neat way to do that. If we use the escape key, we can get some fancy symbols in Mathematica. A relevant one here is the partial derivative symbol, so I hit escape on a new line, type PD for partial derivative. You see it pop up there, hit escape again, and you see we get that little d that we're familiar with. And I want to take the partial derivative of v, of course, but I need to tell it what variable to use. So for that, I need a subscript, and I hold down Control and hit the minus sign to get a subscript box. Let's take the partial derivative with respect to b, hit the arrow to get out of the subscript of v, of b and c here. Again, hold down Shift and hit Enter to evaluate. And look, we get that nice expression there. You see the quotient rule being employed correctly, and we have an easy expression. So there's the one partial derivative we need for the gradient. Of course, I can just go back into that expression, highlight subscript, trade B for C, execute, and I get the other partial derivative there. That's going to get our system of equations equal to 0, 0. I'll show you another trick. If I go back to that same variable, I can kind of do these both at once. If I take in two brackets to make a kind of a list of lists here, part of the eccentricities of Mathematica that I need to do that. But if I evaluate this command, I will get a list of the two partial derivatives, which is, of course, that is the gradient. And all that's left to do is figure out for what values of b and c is this gradient equal to 0. And now, as the real magic happens, we're going to use good old solve command. And I'll copy in that whole string of the gradient there, and I'm going to set it equal. I need two equal signs to compare here. One equal sign is an assignment. operator. So I want to compare these to 0, 0. And then I have to tell it what variables I want it to solve for. That's the second argument here, B and C. Close everything with a square bracket. And if all goes well, we see some solutions. Solve often spits out some error message. We have some relative ways of getting the some critical points. Here, notice here though, C and B have opposite signs for the most part. So we have this solution right here. B is a half, C is a third, and that's the relevant one for what we want to do. And to finish this problem, all I'm going to do is evaluate my function at those values. 1/2, 1/3 is enough, and I get 162. So there's my value, although if I look back now, I realize I am missing something at this stage. What happened to our 1/6? That volume didn't look right to me. If I go back to my original definition, I realize I forgot a 6 in my denominator. So I'll put it back in and just re-execute these guys. Probably should have caught it at that volume stage. Of course, it's just a constant. It'll get carried through all these operations. It does not change the solution, of course. So we just want the gradient still to be 0. But in our last final answer, which is what is the minimum volume here, I'll execute that 27. That's a bit more familiar. And there you have it. The minimal volume you can cut off with a plane through the point 123 is good old 27.